You ever stop to think about what stops the chair you're sitting on from just collapsing? Or how a car engine can run for years and years without just flying apart? Well, the answer is this kind of invisible science that's behind almost every piece of tech we use. It's called machine design, and it's the hidden engineering that literally holds our world together.
I mean, just look at this. A modern jet engine is a symphony of thousands of incredibly precise parts, all spinning at unbelievable speeds, all withstanding insane temperatures and forces. This is engineering at its most extreme.
So that's the big question, right? What is actually stopping this thing from catastrophically failing every single time a plane takes off? And the answer isn't luck, and it's not just guesswork. It's a methodical, rigorous process that is designed from the very beginning to anticipate failure and prevent it.
To really understand how that works, we need to get inside the mind of the designer. We need to look at the blueprint they followed to turn a simple idea into a safe and reliable machine.
Yeah, this whole process, it's not some kind of magic formula. It is a structured, repeatable framework that makes sure nothing is left up to chance. You know that reliability we count on every day? It is 100% intentional.
At the very heart of all of this is the engineering design process. It always starts with a problem, like, say, we need a more efficient engine. From there, it's all about research, brainstorming, prototyping. But the absolutely crucial step is the cycle. You build and you test, then you modify and refine, and you do it over and over and over again until the design is proven to work.
Now, to really get this, it helps to see the difference between a scientist and an engineer. A scientist, their whole goal is to understand the natural world just as it is. But an engineer, their job is to take that understanding and use it to solve a problem, to fundamentally change the world by building something new.
You see, the scientific method is a loop, and it's designed for discovery, right? You observe, you guess, you test, you form a theory. The engineering process, on the other hand, is a direct path with a really clear goal: create a solution that works.
So, once an engineer has a design, what's next? Well, you have to build it out of something, and choosing the right material is without a doubt one of the most critical decisions in the entire process.
You know, this quote from a classic machine design textbook just says it all. You simply can't be a good designer if you're not an expert in materials. The best blueprint in the world is totally useless if it's built from the wrong stuff. Let's go back to our jet engine for a second. Those fan blades are spinning so incredibly fast that the tips are moving near the speed of sound. They need to be unbelievably strong, but also super lightweight. So, what's the perfect material? A titanium alloy. Now, it's expensive for sure, but it is the only thing that can do the job. And that trade-off right there, between cost and performance, that's classic engineering.
And these properties, they're not just vague ideas, they're measured in really precise ways. For instance, this modulus of elasticity you see here, that's just a fancy term for stiffness. Notice how steel is about 3 times stiffer than aluminum? An engineer uses these exact numbers to calculate precisely how a part will bend and deform. It lets them choose the right material for the job, like lightweight aluminum for a plane wing or super stiff steel for a building's frame.
Okay, so how do these material properties actually translate into the real world? Knowing the material is one thing. Knowing how it behaves under pressure is a whole different ballgame. And that brings us to stress, strain, and most importantly, safety. These terms might sound a little complex, but the idea behind them is super simple. Just think about pulling on an elastic band. That internal force resisting your pull, that's stress. And the amount the band actually stretches, that's the strain. Engineers calculate these values to predict exactly how a part is going to behave. So how do engineers guarantee reliability? How do they make sure things don't break? Well, they use something called a factor of safety. Think of it as a calculated buffer, an insurance policy that makes sure a component is stronger than it absolutely needs to be. It's there to handle unexpected loads, little manufacturing imperfections, or just wear and tear over time. And to make that a little more concrete, a factor of safety of 3 is really common. This means that a bridge support, or a crane hook, or an elevator cable is designed to withstand 3 times the maximum load it should ever see in normal use. It is literally an engineered insurance policy.
But even with the right materials and these safety factors, machines can still fail. And understanding why they break is just as important as knowing how to build them. So this is where we start hunting for the weakest link.
And here is a fascinating, kind of counterintuitive truth about all this. Failure doesn't always happen at the point where the force is greatest. No, more often, it starts where the geometry, the actual shape of the part, creates a tiny, hidden point of weakness.
This whole phenomenon has a name. It's called stress concentration. Imagine stress flowing through a part like water in a river. Any sharp corner, or a hole, or a notch is like a big rock in that river. It causes the flow of stress to get all turbulent and concentrate in that one tiny spot, making it way more likely to crack.
Take a look at these splines. They're absolutely essential for transferring power from a shaft to a gear. But every single one of those sharp internal corners is a potential stress concentrator. Designers spend a ton of time analyzing features just like this, adding tiny curves or smooth edges just to smooth out that flow of stress and prevent a catastrophic failure down the line.
All right, so we've designed the individual parts, but a machine is more than just a collection of components, right? They all have to be connected, which brings us to the world of joints and bearings. Fundamentally, you've got two ways to join parts together. You can use a permanent joint like welding, which basically melts the two pieces into one. Or you can use a temporary joint, like a bolt, which is specifically designed to be taken apart. And the choice between them really just depends on the application. Do you ever need to do maintenance or replace a part?
And let's talk about the humble bolt. It is the unsung hero of machine design. Its threads are such a simple but brilliant invention. It's just an inclined plane wrapped around a cylinder. That simple shape multiplies the force you apply with a wrench, creating thousands of pounds of clamping force. It's what holds these massive assemblies together, but still lets you take them apart for maintenance.
And if joints are designed to hold things rigidly together, bearings are what allow them to move. Their whole job is to conquer friction. By placing these tiny, super-hardened balls between a stationary part and a spinning shaft, they replace high-friction sliding with low-friction rolling. It's what allows machines to run smoothly, efficiently, and for a really, really long time.
So from the overall design process to the choice of materials, the calculation of stresses, and the selection of every last nut and bolt, that's the world of machine design. The real question is, now that you've seen what goes into it, what everyday object around you, your bicycle, a coffee maker, even a simple door handle, will you now see as the marvel of engineering it truly is?